Hey everybody, Mr. Lake here with another chemistry lecture video. We have talked about how to write chemical reactions, we've talked about how to balance chemical reaction equations, and now I'd like to talk to you a little bit about how to recognize the 5 most common fundamental types of reactions so that you can recognize them. We're going to jump right into the first one. The first type of reaction that I think it's important for you to be able to recognize is the synthesis reaction. Now, synthesis is a word that means to combine or to build, right? Synthesize means to make something. So a synthesis reaction means taking 2 or sometimes more things and combining them into one thing. So the basic sort of framework for a synthesis reaction would be like what you see at the bottom of the screen here, like compound A and compound B react to form compound AB, which is just a compound made of the 2 of them bonded together. That's a synthesis reaction. By the way, I'm going to just kind of move through this presentation, so if you ever need to pause it so that you can write stuff down, because you should be taking notes on all this, please do. But in case you are rewatching this or reviewing it or trying to just get an overview, I'm just going to keep going. So for each of the different 5 types of chemical reactions, I'm going to give you an example problem, an example reaction, and give you some time to write it and balance it so that we're getting practice on writing and balancing equations in addition to learning the types of reactions. So, and also, for those of you who are coming into school and I will see you in person, I'm also going to demo each of these different 5 types of reactions. So the first reaction up is solid magnesium and oxygen gas combined to form solid magnesium oxide. So pause the video, take as long as you need to write that out and balance it. And I'll come back in a few seconds and show you what that looks like. I hope you paused the video and did that balancing and that writing. Let me show you what this looks like. We're going to do blue. All right, so solid magnesium, that's going to be Mg, and we're going to put an S below it because it's a solid. Now, because it's a element by itself, we need to mentally go through that list of diatomic elements and try and remember, is that something we need to write a 2 after or not? So the mnemonic device that I use is I have no bright or clever friends. So I think through those 7 elements. So I have no bright or clever friends. None of those are magnesium, so I'm just going to leave it like that with no subscript 2. So solid magnesium and oxygen gas. Let's think back through that list of diatomic elements. I have no bright or clever friends. So oxygen is one of the diatomic elements. You need to write a 2 after it. Those things combine to form solid magnesium oxide. That's an ionic compound. So we've got to think about what would that ionic compound be. Dig out your periodic table. The magnesium is going to be the cation. It's in the second column. So it's got a +2 charge. Oxide is oxygen, which is in the third to last column, so it has a -2 charge. So when those things come together, if you cross drop or if you think about how to simplify and make it so that it's an ionic compound with a neutral overall charge, it's just going to be 1 magnesium and 1 oxygen that come together. Because a 2+ and a 2- will neutralize each other. Oh, and it's a solid. So that's how you write this chemical reaction formula. Sorry, chemical reaction equation. Now, I'm going to switch colors and we're going to balance it. Because this may or may not be the actual representation of what truly goes on at a molecular level. In order to really have an accurate representation, we need to balance this thing and make sure that it all checks out. So To balance, I recommend making a T-chart with reactants on the left, products on the right, and then along the left-hand side, write out all of the different elements that are involved in the reaction and total up how many are on the reactants and the product side. So in the reactants, there's currently 1 magnesium and 2 oxygen atoms. And in the products, there's 1 magnesium and 1 oxygen. So these are not balanced. This is not actually representative of what's going to happen at a molecular level. We have to make it balanced. So first of all, I'm seeing that we need to have more oxygen in the product side. So since I want to have 2, I'm going to try putting a 2 here in front of magnesium oxide, which is going to change the number of magnesium to 2 as well as the number of oxygen to 2. Which means now the magnesium is imbalanced, but if I go over here and I put a 2 in front of this magnesium, that bumps the number of magnesium up, and now we have equal numbers of atoms of each element on both sides of the equation. So we have a fully balanced chemical reaction equation. This is what's really going to happen at a molecular level or an atomic level. 2 magnesium atoms will react with 1 diatomic oxygen molecule to form 2 magnesium oxide atoms. If you just had 1 magnesium and 1 O2, you could not perform this reaction. You would not have enough to create a product where the law of conservation of mass was followed and that the whole entire reaction was self-contained. So that's the first type of reaction, the synthesis reaction. The second type of reaction that we're going to go over is also kind of a synthesis reaction, but it's like a special type of synthesis reaction called a combustion reaction. This is everybody's favorite. This is fire or explosions. But all of those different explosions that you've seen in your life on movies and stuff like that, and all the different forms of flame and, applications of fire, it's all combustion. And combustion is actually a very specific type of reaction. It's a reaction where oxygen, usually from the air, reacts with a substance, usually something very rich in carbons and hydrogens, like a carbohydrate or a carbon-rich molecule. And in the process of reacting, they form water, carbon dioxide, and also heat and light, which are either, depending on how quickly the reaction goes, is either a flame or an explosion. If it's a really slow reaction that releases that energy over time, the heat and the light are a flame. If it's a very fast reaction that releases a lot of energy all at the same time, it's an explosion. So the basic sort of framework equation for what a combustion reaction is it's a carbon-hydrogen rich molecule reacting with oxygen gas to form carbon dioxide and water. Oftentimes you don't write energies as part of the chemical equation because they're not matter, but we could go over here and add, plus heat plus light, because those are very, very commonly also things that are produced from this reaction, even though they're not products because they don't have mass. That's part of the process. So the example that I'd like you to work on for the next couple of minutes, writing it and balancing it, is the reaction of carbon tetrahydride, also known as methane, and oxygen to form carbon dioxide and dihydrogen monoxide. So pause the video, write that out, balance it, and then play the video when you want to check your work. Let's go through it together. Carbon tetrahydride, that's a covalent compound because it has a prefix in it. So that means that it is 1 carbon, 4 hydrogen. Sorry, I had to try and remember. For a second, I doubted myself that tetra was 4, but it is. Carbon tetrahydride, aka methane, and oxygen. Now, we're not being given any states of matter here, so we're not going to include any subscript letters. It's just carbon tetrahydride and oxygen. Now, that's an element by itself. I need to go through my list of diatomic elements. I have no bright or clever friends. Oxygen is a diatomic element. And those react to form carbon dioxide, another covalent compound with 1 carbon, 2 oxygens, and dihydrogen monoxide, another covalent compound with 2 hydrogens, 1 oxygen. Now, why didn't I just call that water? Because I want you to practice your covalent compound stuff. So that is what we call the skeletal equation of this reaction. Now, let's go through the balancing process. And if you want to pause the video so you can try balancing it yourself, please do, but I'm going to jump right into it. Let's do green for this balancing. All right, reactants, products, T-chart. I always struggle with making the vertical line straight. Carbon, hydrogen, and oxygen are the 3 elements that I see involved in this reaction. On the reactant side, there's currently 1 carbon, 4 hydrogens, and 2 oxygens. And on the product side, there's 1 carbon. Oh, this is interesting. There's oxygen in 2 different places. So there's a total of 3 oxygens and 2 hydrogens. When that's the case, when there is the same element in multiple different compounds on one side of the equation, you've got to just be a little bit slower and a little bit more methodical with your balancing, because if you choose the wrong thing to change a coefficient for, you could kind of end up in this like feedback loop. If that's ever happened to you, you know what I'm talking about. So I see that I need more hydrogen on the product side. In fact, I need twice as much hydrogen on the product side. So I'm going to try throwing a 2 in front of the H2O. That's going to up the number of hydrogens in the products to 4. It's also going to change the number of oxygens to a total of 4. So now my oxygens are imbalanced, and luckily I can just change the amount of oxygen by throwing a coefficient there. If I put a 2, it'll up the number to 4. So this is the balanced reaction of methane and oxygen to form carbon dioxide and water. So it's going to take 1 molecule of methane, 2 molecules of diatomic oxygen. They will react to form 1 molecule of carbon dioxide and 2 molecules of H2O. It might seem like nitpicky or something to demand that things are balanced, but it's not. It's really important that when you're thinking about a reaction that takes place, that it's actually representative of exactly what would happen at the molecular level. Here's an image that just breaks down that last one. So if you're a visual person, I found this somewhat blurry image on the internet of this exact reaction. And what you can see is that, well, then the colors of different things changed, but there's the same number of atoms of all the different types of elements on both sides of this reaction. This is also kind of interesting because it does show you the molecular geometry of these different things. So we haven't gotten into that, but methane has a tetrahedral shape over here. Oxygen is actually double bonded oxygens to one another in a linear shape. Carbon dioxide has a linear shape. And water has this bent shape that's interesting. These two blue dots are representing lone pair electrons that are pushing the hydrogens kind of away from that area and bending the molecule. So instead of being straight like CO2, it's bent like this, which is actually really important to life and the world and stuff, because that bent nature of water kind of creates this polar nature of water, which is why things dissolve, and it's why, anyway, I'm getting way, way ahead of myself. If none of that made sense, don't worry about it. But if any of that kind of like interested you, we're hopefully going to talk about some more of that later on in chemistry, and also we will talk about it more if you take future chemistry classes. Reaction type number 3 is called a decomposition reaction. This is the opposite of a synthesis reaction. In a synthesis reaction, two things combine to form one thing. In a decomposition reaction, a single compound breaks into two or sometimes more elements or compounds. So this framework down here would be like if compound BC broke into compound B and compound C. I also really like what they did here, where it was purple breaking down into blue and red. Clever. Very, very clever. Let's look at an example. Actually, first, sorry, I forgot that I needed to clarify this. Decomposition often doesn't happen just spontaneously. So if you just have a compound sitting there, it doesn't often just randomly start breaking up into pieces. If it's stable and it's sitting there, it kind of actually means that it's not going to do that. So decomposition usually requires some sort of an input of energy. So like if you heat something up, then it starts to break apart. Or if you shine a really bright light on it or a certain wavelength of laser or something like that, then it starts to break apart. Or if you run electricity through the sample, that will provide the energy to start breaking those bonds and causing that thing to break apart. So decomposition usually requires an input of energy. Here's the example I'd like you to go through, write it, and balance it. In the presence of electricity, water decomposes into hydrogen and oxygen. Take a few moments, write that out, balance it, pause the video for the meantime, and press play when you're ready to check your answer. I'm back. Let's go through this. In the presence of electricity, do we have to include that in our reaction? We don't really, because electricity is energy. So I'll show you a way that sometimes an input of energy is indicated while you're writing a chemical reaction. So water decomposes into hydrogen and oxygen. That's the real reaction we're dealing with. And I did not call it dihydrogen monoxide. I just called it water, but hopefully you know that water is H2O. And that's going to decompose, and I'm drawing a long arrow for a reason that I'll explain in just a minute, into hydrogen and oxygen. Now, since those are elements by themselves, we need to go through the diatomic list again. I have no bright or clever friends. Hydrogen and oxygen are both diatomic elements, so they're not going to be by themselves. They're always going to have a 2 after them when they're alone, only when they're alone. Now, the reason that I wrote a really long arrow here is because sometimes when you input energy into a reaction, you put it over the arrow, saying that at least this is what I do. Maybe this isn't something that everybody does, but sometimes I will do this to say H2O, when you expose it to a bunch of electricity, it causes it to break into these things. So you're representing the energy there, but you're not including it like it's a product or a reactant. You're just including it as this is the thing that causes the arrow to occur. It causes the reaction to happen. And now you have to balance it. Hydrogen and oxygen are the only elements that are in this reaction. Currently, there are 2 hydrogens and 1 oxygen in the reactants, 2 hydrogens and 2 oxygens in the products. So we need more oxygen in the reactants. Let's throw a 2 in front of H2O. That's going to change the oxygen to 2, but it's also going to change hydrogen to 4, which means we then have to put a 2 in front of the H2 on the product side to get it all balanced. So now that is a balanced reaction. And here's a visual of that happening, which visuals are kind of nice because you can really see why the balanced reaction is important, so that there's none of the atoms are lost. No atoms are randomly produced out of nowhere, which is impossible. in the reaction. And everything finds its place. Now, we're on to number 4 out of 5 of the different types of reactions. This is where it gets a little bit more interesting. Type number 4 is called a single replacement, or you can call it a single displacement reaction. And this is where a pure element reacts with a compound and takes the place of an element in that compound. So for example, let's say that element B and C are bonded together. Element A comes in and basically takes B's place. So now you have compound AC and element B is off on its own. So it's almost like an element is stepping in and stealing the partner of something else that was there. So it's kind of like this very sad example of, someone cutting in on the dance floor. People don't really dance like this anymore, so you don't really see it, but, maybe that's for the best. Pretty upsetting. So here's an example. And this is where you're going to have to flex your ionic compound knowledge skills. Silver 1 nitrate and copper react to produce copper 2 nitrate and silver. Pause the video, write out that reaction, balance it, hit play when you're ready to check your answer. Okay, I hope you gave this a try. It's really important that you be able to do these things on your own, but I'm going to walk you through how to do it right now. Silver 1, well, first of all, silver is Ag, and the 1 in one Roman numeral in parentheses means that it has a +1 charge. Nitrate is one of the polyatomic ions, so I'm going to look that up on my polyatomic ion chart, and it's NO3 with a -1 charge. So when silver 1 and nitrate come together, they are going to form the compound AgNO3. You just need one of each because a 1 plus and a 1 minus will cancel each other out. That's going to react with copper, which is Cu. Now, since it's by itself, I have to go through my list of diatomic elements. I have no bright or clever friends. Copper is not one of those 7 elements, so I'm just going to leave it like that and not put a 2 after it. Those things react to form copper 2 nitrate and silver. So copper 2, I'm going to write this over here. Copper 2 is copper with a 2 plus charge, and nitrate, as we already established, is NO3 with a -1 charge. So when those things form a compound, you're going to need 2 of the nitrates to cancel out the 2 plus charge from the copper, or you can think you're going to cross drop. So it's actually going to be CuNO3 2. And silver is the other product. So again, since it's by itself, I've got to go through my list. I have no bright or clever friends. Silver is not one of those 7 elements, so I'm going to leave it like that with no 2. Oh boy, what a doozy. Now we have to balance it. So I'm going to make my T-chart, reactants, products. The elements that I see, there's a whole bunch of them. We've got silver, nitrogen, oxygen. Now, technically, you could balance this with nitrate. When the polyatomic ion isn't broken up, you could just balance it with the polyatomic ion. I'm probably not making any sense. I'm just going to go with the way that we've done it and think about individual elements. So we've got silver, nitrogen, oxygen, and copper. Those are our 4 elements that we're dealing with. On the reactant side, there's currently 1 silver, 1 nitrogen, 3 oxygens, 1 copper. And on the products, there's 1 copper. This applies to everything in parentheses, so there's 2 nitrogens, 6 oxygens, and 1 silver. So our imbalance is in the nitrogen-oxygen department currently. So we need more nitrogen and more oxygen on the reactant side. And since this is the nitrogen-oxygen containing compound, I'm going to put a 2 here and see what happens. Update my T-chart. So now there's 2 silvers. And this again applies to everything. So there's 2 silvers, 2 nitrogens, and 6 oxygens. Oh man, that almost did it, but it threw silver out of balance. Luckily, we can just put a 2 over here in front of the silver and make everything balanced. So what you might be noticing is that when you balance equations, the most common prefixes you'll end up with, coefficients that you'll end up with are 1, 2, 3. Like 80% of the time, those are the coefficients you're dealing with. Sometimes 4, not saying it couldn't be 5, 6, or even more, but like most of the time, you're like adding a 2 or maybe a 3 in front of something to make the whole thing balanced. So there you have it. That is the balanced equation for our example of a single replacement reaction. Now, before we move on to the 5th type of reaction, I have to bring up the activity series, which is in your survival guide. You've had this since the beginning of Chemistry A. The activity series is basically a list of a bunch of elements, mostly metals, in their order of reactivity, with the most reactive stuff being at the top and the least reactive stuff being at the bottom. Why this is important is that when it comes to these single replacement reactions, it's usually a metal that is coming in and kicking out another metal from being in a compound. It's only going to do that, though, if the metal that's coming in is more reactive than the metal that's already in the compound. If it's less reactive, then nothing will happen. So, for example, if I were to ask, will lithium replace aluminum? You would want to go to, like, if we had a compound where it was like, I'm just going to make something up, I don't know, aluminum chloride, and you threw some lithium in there, would it react to form lithium chloride and kick the aluminum out? Would that happen? Well, what we'd have to do is we have to go and find lithium and aluminum. So there's lithium and there's aluminum on the chart. Lithium is more reactive than aluminum. So this is going to happen. This is going to happen because lithium is more reactive than aluminum. So it's going to go in and kick aluminum to the curb and take its place. Now, will aluminum replace calcium? So if we had like calcium chloride, and we threw some aluminum in there, would that aluminum take the place of the calcium and form aluminum chloride and kick the calcium out? Well, aluminum is here, calcium is here, so aluminum is not as reactive as calcium, so this is actually not going to happen. If you did this, there would be no reaction. The aluminum would just sit there in the calcium chloride and do nothing because it's not reactive enough to take the place of the calcium. Let's do one more, all right? Here's the question. Will silver replace tin? Pause the video, think about it, get an answer, press play when you're ready. Okay, silver is Ag, and it's over here. On the activity series, tin is Sn. So would silver replace tin? No, it would not, because it is less reactive than tin. Now, if the question was, would tin replace silver, the answer would be yes, but not the other way around. So that is something that you need to know about these single replacement reactions, is that it all has to do with reactivity. And sometimes it's not guaranteed to happen. It's only basically whatever is most reactive wins. You can think of it that way. Whatever is most reactive wins and gets to be with the anion. Oh, I guess we've got another one. I forgot there was another example. Okay, will iron replace lead? Think about this one really quick. You can pause the video if you want to. Iron is over here. Lead is down here. Yes, it will. Iron is more reactive than lead. I'm also throwing these examples at you because I want you to get used to some of the elements where the symbol does not match the name, right? Like iron is Fe, lead is Pb, tin is Sn, silver is Ag. It all has to do with like Latin in their previous names, or sometimes just because the other letters were taken, or you just have to get used to some of the weird elements. Now we get on to our fifth and last reaction type. So this is reaction type number 5, the double replacement, or you could call it a double displacement reaction. And this is where you have two ionic compounds and they find each other and they switch partners. So the cation from one ends up bonded to the anion from the other and vice versa. So if you had, for example, compound AX and compound BY, they would come together, react, and you'd end up with compound AY and BX. They switched partners. So here's a great example of a double replacement reaction. Sorry, I couldn't help myself, although I know that this example is a little bit dated. Okay. There is actually some chemistry here on the bottom that represents a real double replacement reaction, but I'm sure that was not really the point of that slide. I just wanted to make that joke. Okay, here, whoops. Here is our example of a double replacement reaction. So please go ahead and pause the video, write this out. It's going to take a little bit, but pause the video, write this out, and balance it. Press play when you're ready. Okay, I hope you're ready. Potassium iodide. That's an ionic compound because it's got a metal and a nonmetal and it ends in "ide." So I know that's a ionic compound, and I'm going to have to do the whole ionic compound solving thing. So I'm actually going to write the formula in this empty space here and just going to do my scratch work down at the bottom. So potassium is K. It's in the first column of the periodic table, so it's got a +1 charge. Iodine is iodine. Iodide is iodine, which is in the second to last column of the periodic table, so it has a -1 charge. So potassium iodide is just Ki. That's going to react with lead 2 nitrate. Okay, so lead is Pb, and since it's a 2, it's got a 2+ charge. Nitrate is one of the polyatomic ions, so I've got to look that up. Nitrate is NO3 with a -1 charge. When you cross-drop those things and they come together, it's going to be 1 lead, 2 nitrates. Those react to produce potassium nitrate. So we've got potassium with a plus charge and nitrate with a negative charge coming together. So it's just going to be one of each, potassium nitrate. And lead 2 iodide. So lead with a 2+ charge, iodine with a -1 charge. So lead 2 iodide, cross drop, and it's going to be 1 lead, 2 iodides. That's our skeletal equation. Now let's balance it. We're going Superman colors here. Reactants, products, T, chart. There's a bunch of elements here. Potassium, iodine, lead, nitrogen, and oxygen. Holy moly. In the reactants, there's 1 potassium, 1 iodine, 1 lead, 2 nitrogens, and 6 oxygens. In the products, there's 1 potassium, 1 nitrogen, 3 oxygens, 1 lead, and 2 iodines. All right, so we need a balance. I'm just going to kind of work my way down this list because normally I would say try and balance the bigger compounds first, but all of these are multi-atom compounds, and so I'm just going to work my way down the list. And the first thing I see that's imbalanced is iodine, so I'm just going to add some more to the left-hand side. Put a 2 there. That changes potassium to 2 and iodine to 2. Well, I balanced one thing and got something else unbalanced, but I'm going to keep going with it, see where it goes. Okay, so now my potassium's unbalanced, so let's try maybe adding a 2 over here. That's going to up the number of potassiums to 2 on the product side, the number of nitrogens to 2, and the number of oxygens to 6. Sweet. That did it. That balanced the equation. So there you have it. Those are the 5 types of standard fundamental reactions. We did writing and balancing practice with every single one. And if you were in class, or if you come into class, you probably also saw those reactions demoed. So that was a lot. It's a lot of new information. This is not just one day worth of information. We're covering this in a couple of different days. But I'm going to end the video here because it's getting a little bit long. So take care. Until next time, have a great one.